Let's talk about a discovery that completely changed our view of the universe. Imagine standing beneath a vast star-filled sky, wondering what lies beyond. For most of human history, we believed the cosmos was a simple, predictable place, governed by rules that seemed obvious to our senses. For centuries we saw space as empty and time as a universal clock, simple, intuitive, and the basis of Newton's physics. Newton's laws explained the motion of planets and falling apples, and for generations this view shaped our understanding of reality. Space was a stage, time ticked forward, and everything moved according to these unchanging rules. Then Einstein came along and rewrote the rules. He dared to question what everyone thought was certain, and his curiosity led to a radical new vision of the universe. He revealed that space and time are not separate, they're woven together into a single, four-dimensional fabric, SpaceTime. This fabric can stretch, bend, and ripple, connecting everything in the universe in ways we never imagined. This wasn't just a tweak, it was a revolution that changed how we understand gravity, motion, and reality itself. Suddenly the universe became a dynamic, interconnected place where even the passage of time could change depending on where you are and how fast you're moving. Massive objects don't just move through space, they bend and curve space-time, and that's what we experience as gravity. The sun, planets, and even Earth itself are shaping the very fabric around them, guiding the paths of everything nearby. When you drop your keys, they're following the straightest path through curved space-time, not being pulled by a mysterious force. It's as if the ground rises up to meet them, guided by the invisible curves of the universe itself. This idea is the heart of general relativity, a theory that underpins everything from black holes to the GPS in your phone. Without Einstein's insights, our technology and our understanding of the cosmos would be stuck in the past. So buckle up, we're about to dive into the fabric of reality and see how Einstein's ideas shape our understanding of the cosmos. Get ready to explore a universe far stranger and more beautiful than anyone ever imagined. So, what is space-time? Let's break it down. We know three dimensions, length, width, and height, enough to locate anything in space. But Einstein realized you need a fourth time. To describe any event, you need to know where and when it happens. Space and time together form a four-dimensional framework, space-time. Imagine it as a flexible grid that can be stretched and curved. Matter and energy tell this fabric how to bend, and the curvature tells matter how to move. This is the core of general relativity. Matter curves space-time, and curved space-time guides matter. Space and time are not absolute, they're relative, depending on your motion. Move fast, and your experience of space and time changes. They're not universal but personal, shaped by your path through space-time. This interconnectedness is the key to understanding gravity and the universe. It's the foundation for unlocking the cosmos's deepest secrets. How does a flexible space-time fabric explain gravity? To answer this, we need to rethink what we know about the universe. Imagine space not as an empty void, but as a dynamic, flexible fabric that can bend and stretch. This idea is at the heart of one of the most revolutionary scientific breakthroughs of the 20th century. Here's where Einstein's theory shines. He realized that gravity isn't just a mysterious force acting at a distance, but something much deeper and more elegant. Newton saw gravity as a force pulling objects together, but Einstein said it's not a force at all. Instead, he proposed that massive objects like stars and planets actually warp the very fabric of space and time around them. Instead, gravity is the effect of curved space-time. The more massive the object, the greater the curve it creates. Picture a trampoline. Put a heavy ball in the center and it warps the surface. The heavier the ball, the deeper the dip in the trampoline. Roll marbles nearby and they spiral inward, not because of a force, but because they follow the curved surface. Their paths are straight lines on a curved landscape, which makes them appear to be pulled in. That's how planets orbit stars. They're following straight paths in curved space-time. The sun's mass bends the space around it, guiding the planets along their orbits. Even light bends when it passes near massive objects, a phenomenon called gravitational lensing. This effect lets us see distant galaxies magnified and distorted by the gravity of objects in between. This has been observed and confirms Einstein's theory. Astronomers have seen starlight curve around the sun during eclipses, and telescopes capture the warping of light from faraway galaxies. Gravity isn't a mysterious pull, it's geometry in action. The universe is shaped by the presence of mass and energy, and everything moves according to the curves in this cosmic fabric. The sun warps spacetime, and Earth moves along the curves. This is why our planet orbits the sun year after year, following the invisible contours of spacetime. The same goes for every object in the universe. From tiny moons to massive galaxies, all are guided by the shape of spacetime itself. The trampoline analogy helps us see, gravity is the shape of spacetime, not a force. It's a new way of thinking that changes how we see the cosmos. This insight changed physics forever. It opened the door to understanding black holes, the expansion of the universe, and even the possibility of time travel. It's the reason we can understand orbits, black holes, and more. Einstein's vision of a flexible, dynamic spacetime continues to shape our exploration of the universe today. Let's dig deeper. Gravity isn't a force, but a result of geometry. This idea might sound strange at first because we're so used to thinking of gravity as a mysterious pull, an invisible hand that tugs everything downward. But what if instead gravity is simply the way space and time themselves are shaped? In Newton's view, gravity pulls objects off their straight paths. He imagined a force reaching across space, causing apples to fall and planets to orbit. For centuries this idea worked well, explaining everything from falling objects to the motion of the moon. But Einstein saw it differently. Objects in free fall aren't feeling a force, they're following the natural curves of spacetime. Imagine spacetime as a giant, flexible fabric. When a massive object like Earth sits on this fabric, it creates a dip, and smaller objects move along the curves created by that dip. Astronauts in orbit feel weightless because they're in free fall, moving along these curves. They're not being pulled by an invisible force, but are simply gliding along the straightest possible path in a curved spacetime. You only feel gravity when something stops you from falling, like the ground pushing up on you. If the floor vanished, you'd float, just like the astronauts, following the curve of spacetime. That sensation isn't gravity pulling you down, but the ground pushing up, resisting your natural path. The pressure you feel in your legs is the ground's upward force, not gravity's downward pull. The sun doesn't reach out to grab Earth, it simply warps spacetime, and Earth responds to that curvature. Planets orbit not because they're being pulled, but because they're following the straightest paths possible in a warped geometry. If the sun vanished, the change in spacetime would ripple out at light speed. Gravity isn't instantaneous. These ripples are what we call gravitational waves, and they travel just like light does, carrying information about changes in the universe. This geometric view solved Newton's action at a distance puzzle. No longer do we need to imagine invisible forces acting instantly across empty space. Gravity is local, dictated by the shape of spacetime. Every valley, every curve, every dip in this fabric tells matter how to move. The force you feel standing is the ground's push, not gravity itself. Your weight is a measure of how much the ground resists your natural motion through curved spacetime. This flips our intuition and reveals the true nature of gravity. It's not a force acting at a distance, but a feature of the universe's geometry. It's a mind-bending shift, but it matches what we observe. Experiments and astronomical observations confirm Einstein's predictions, from bending starlight to the dance of galaxies. The universe is shaped by geometry, not invisible forces. Every star, planet, and galaxy moves according to the curves and contours of spacetime itself. That's the genius of Einstein's insight, a new way to see the cosmos, where the fabric of reality itself guides the motion of everything within it. Here's where relativity gets truly strange. Warping space also warps time. Time dilation means time can pass at different rates for different observers. There's no universal clock. Your time and mind can tick differently. Move fast, and your clock slows down. This is special relativity. If you travel near light speed, you age less than someone who stays on Earth. This twin paradox is real and measurable. General relativity adds that gravity also slows time. Clocks closer to massive objects tick slower than those farther away. A clock at sea level runs slower than one on a mountain. Near a black hole, time nearly stops. Time is not steady. It flows differently depending on speed and gravity. This isn't just theory, it's been measured and confirmed. Time and space are inseparable, and both are flexible. Does any of this matter in daily life? Absolutely. GPS relies on Einstein's relativity to work. Satellites orbiting Earth have precise clocks, but their speed and weaker gravity make their clocks tick differently than those on the ground. Special relativity makes satellite clocks run slower, general relativity makes them run faster. The net effect satellite clocks gain about 38 microseconds per day. Without correcting for this, GPS would be wildly inaccurate within minutes. Engineers built these corrections into the system. Every time you use your phone for directions, you're relying on relativity. Abstract physics has become essential technology. Einstein's ideas shape our world in ways we use every day. One of relativity's wildest ideas is that now isn't universal. Two events that seem simultaneous to one observer may not be for another moving observer. Imagine lightning strikes at both ends of a train as it passes a platform. The person on the platform sees both flashes at once, simultaneous. But a passenger on the moving train sees one flash before the other. Who's right? Both are from their own perspective. Simultaneity is relative, not absolute. There's no single now across the universe. Your present is defined by your motion through space-time. This forces us to rethink past, present, and future. General relativity's power is clearest with black holes and gravitational waves. A black hole forms when matter is packed so densely, it warps space-time into a bottomless pit. Inside the event horizon, nothing, not even light, can escape. Time and space swap roles, the singularity becomes the inevitable future. Black holes are real, predicted by Einstein long before we observe them. Gravitational waves are ripples in space-time from massive objects in motion like merging black holes. Einstein predicted them, and in 2015, LIGO detected them from two colliding black holes. These discoveries confirm space-time's dynamic nature. Black holes and gravitational waves are not just theory, they're observed realities. They open new windows to the universe. Einstein's equations continue to reveal the cosmos's most extreme secrets. From falling apples to colliding black holes, space-time has transformed our view of the universe. Einstein gave us a new language. Space, time, matter, and energy are all part of one cosmic conversation. We've learned that time stretches and shrinks, and gravity is the shape of the universe itself. These ideas power technologies like GPS and explain cosmic phenomena. Space-time is the foundation of modern cosmology, letting us study the universe's origins and fate. Every time we look at the stars, we're peering through warped space and time. Learning about space-time is humbling and awe-inspiring. It reveals a universe more intricate and elegant than we ever imagined. We're not just in the cosmos, we're part of its geometry. And that's one of the most beautiful ideas in all of science.